Okay, we stopped here last time. We were talking about the allowance in casting. Still, we are talking about casting. Allowance in casting. Allowance means shrinkage allowance, machining allowance, with draft allowance. Three allowance. Shrinkage coming from solidification, machining later after you complete the process. You need to do machining to remove the outer layer and inner layer. Huh? Remove two layer, outer layer and inner layer, because especially in sand casting, because diffusion happen and some sand trap inside. Then you get a layer, outer layer and inner layer mix of liquid and sand you need to remove. So this is the machining. We remove the outer layer and inner layer. And also shrinkage means that the part, as you can see here, after solidification, dimension is getting smaller. Then you need to make it bigger. You need to make it bigger dimension. Draft allowance, which is the angle to facilitate the part, taking part out from the mold easily. Then start one by one. Last time we discussed about the machining allowance. This is the machining allowance. We said that machining allowance is known. As I told you before, we know the amount of layer of machining that required to machine. For example, 3 millimeter for cast iron, 3 millimeter to all surfaces. Then every dimension here, as we described last time, every dimension here will increase 3 millimeter. So you have here, you can see that this is 150, this is 75, this is 50 millimeter, this is 200 millimeter, this is 100 millimeter. All these dimension will change, as you can see here, as we described last time. So 150 millimeter, we added 2 multiplied by 3, because we added 3 in this dimension and 3 here. This is 150 millimeter. We added 3 here, and we added 3 here, 3 millimeter here. Then you added 6 millimeters, then 150 increased to become 156. 100 millimeter, this is 100 millimeter, whereas 100 is here. This is 100 millimeter. So this 100 millimeter, as you can see, also 100 millimeter will increase also 6 millimeter up and down. In diameter we put 3 millimeter and 3 millimeters, then 6 millimeter in diameter, 3 millimeter in radius, then become 106. 75, which is the hole inside. This hole inside, actually we subtract. We will not add it, we subtract, because the hole, we need to make it smaller, not bigger. Smaller, then when we remove the material become bigger. Then we need to remove the material. So here, in case of the whole bigger dimension, if you talk about the outer surface we added dimension. So when you do machining, you remove the layer, but inner surface we subtract because make it smaller. Then when you remove the material, then make it bigger. Then only hole, when you talk about 75, you subtract 6 millimeter, 200 millimeter, which is this one, this 200 millimeter, they added 3 millimeter and 3 millimeter, become 26, and 50 millimeter, which is this length, you added 3 millimeter and 3 millimeter, is in 56. That's what we described last time. This is in case of machining allowance. Next is we stop here, shrinkage allowance. Shrinkage allowance is very simple. Actually, it is also known, shrinkage allowance is also known, allowance is 0.8 millimeter for 100 millimeter in core. For core, if you talk about the core, which is the inner dimension, 0.8 millimeter for 100. If you talk about the length or dimension, 1 millimeter for every 100 millimeter. Then, okay, let's see how to, this kind of percentage. It's kind of percentage. It be usually described like a percentage of the dimension. And this also for certain material, which is cast iron, it is different. If you talk about aluminium, if you talk about copper and so on, and this dimension, all this dimension is described based on the behavior of the material in the shrinkage. Then shrinkage, if you see the shrinkage here, you can see that shrinkage material will shrink. Material will shrink dimension, all dimension is getting smaller. All dimension, whether it is internal dimension or external dimension. So all external dimension and all internal dimension will getting smaller. Getting smaller, then we need to increase. We need to add it. this kind of allowance, then make it bigger, then make dimension bigger. Later, while solidification, when this part shrink, then dimension will be okay. Then you need to start actually from the dimensions that you had here. So we need not to start from here for machining, we start from this one. Then we're going to use this kind of dimension. We added to this dimension which is obtained after adding machining allowance. This is a dimension after adding machining allowance. We will start from this one in shrinkage allowance. So this one become 26, 156 and so on. Then this dimension will added the shrinkage allowance. So start one by one. This 156, this dimension diameter, this diameter 156, and we said the length is 1 millimeter for 100, then 0.01 or 1 for 100 for 156. Then you see it's kind of percentage of 156, which is this one. Then you get 158, then this one become 158, increase the dimension. 106 also, this is the other diameter is 106, which is this diameter. Can you see that? Also we multiply by 0.01, which is a percentage, 1%. 1% multiplied by 106, then you get this. So all dimension, even internal dimension, which is this one, core is 69. 69 as a core multiplied by zero point 0.8 for 100, because this is a core, this is the length. Then 0.8 for 100 for 69, then you get the core, new core. You need to add it, Ahmed, just give me a second to finish this one. You need to add it here. For all dimension, you need to add it. 206, this one increase become 208, and 56, this one increase to become 56.6. Yes, Ahmed, I'm listening.
Yes, doctor. For the inner diameter, why we don't subtract like the machining
Because
allowance?
it is shrink here. Dimension is getting smaller. You need to make it bigger because, do you see that? This is photo. Let me show you the next one. This is the one. Initially core like this, right?
Yes,
Right? You listen to me. So
yes.
this is a core, right? This is a core. So you see, it is initially big, right? What happened later? What happened later?
It
It's getting
shrink.
smaller.
I understand. Okay.
So you need to add it. You need to make it bigger. You need to make it bigger. You need to add it to make it bigger. So later it becomes smaller. You understand me?
Yes, yes.
It is opposite of machining. So be careful about this one. So here you need to add it. You need to add it all dimension actually. I put this photo to make it easy for you. I make this shrinkage photo so you can imagine what happening. So this is the shrinkage allowance, right? Any question, guys? Any question? So here you can see in this photo I make it for you. This is initially shrinkage. You see all the image getting smaller. Even this one, all the dimension is getting smaller. This is a part here. The dash line is the one happen after shrinkage. You can see that all dimension is getting smaller. So this is the shrinkage allowance. And finally is the taper allowance. Taper allowance, you need to make it taper here. Why we do taper? To facilitate. Only the reason to added draft allowance is to make it easy. This dimension being added only to easy take the part out of sand, as we described. Then we make the taper. Then this every surface here will make it taper. So for example here like this. So this surface will make taper here. 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 Can you see that? So we'll make taper here and here and here and here. The only reason is to easily take the part out from sand. Also internal surface will make taper. How to make taper actually? Make taper is like this. and make taper like this. Internal hole will try to make also taper like this. Then easily you can just take it out from the sand. This is the idea. Then the taper, he described taper 1% for external, 2% for internal. 2% of the length actually. Then 158, this is 158 diameter. This is 158. 2% of the 56 because you added here and you add here. So this is 2% of 56.6. Then 2% here you added here. Then one here and one here. Then two part, one in this side, one in this side. 2% or 1%, sorry, 1% of 56.6. Yes, Muhammad.
Doctor, why do we multiply by 2 for 158 although we have only one side. مثلا ال 56 عندنا فوق وتحت بس ال 158 ما عندنا جهة واحدة.
ايوه مظبوط، ما هي 158 زائد، يعني 158 دي معانا زائد 2 الحته اللي فوق دي والحته اللي تحت دي.
بس هذه مو ال 56.
ما هي دي نسبه من ال 56 يا محمد، يعني هي 1% من 56. يعني الحته دي هي 1% من 56 والحته دي هي 1% من 56. يعني عندك حتتين، الجزء اللي فوق ده والجزء اللي تحت ده. دي 1% of 56 1% of 56 يبقى 2 حتتين هنا وهنا، يبقى 2 ملتبلايد في الحته دي. ماشي.
طيب عند الشرينكج طيب كيف كانت؟
لا الشرينكج احنا ضفناه خلاص. ده الدايمنشن دي بعد ما ضفنا الشرينكج والماشينينج.
ايه طيب
يعني
بس
احنا
بيعرف كيف صارت عند الشرينكج نفسه قبل.
ما خلاص انت هتشيلها بالماشينينج ليتر، يعني دي هتبقى جزء من الماشينينج هتشيلها.
اوكي.
يعني الدايمنشن اللي عندك ال 158 دي هي بعد ما انت ضفت الماشينينج الاونس والشرينكج الاونس. يعني نمره واحد انت ضفت الماشينينج، نمره اثنين انت ضفت الشرينكج، بعد كده بتضيف الدرافت الاونس. يعني الدايمنشن دي هي عباره عن مجموع الاثنين اللي كانوا قبل كده، بعد كده بتضيف الحته دي عشان تبقى دي الدرافت الاونس. دي جت محمد سامعني؟
Yes, thank you.
Someone said that dimension will now become very big. Okay, it's more safe because if you do the casting process and dimension getting smaller than what is needed, then it is scrap. We need to avoid having scrap. Someone also will ask me, we have a riser and this riser usually deliver liquid to compensate shrinkage and so on. This is for more safe. Yes, I understand, but if riser not working for any reason, then we have to be sure that the part will, the dimension of the part and geometry of the part will be satisfying the condition. We don't want to leave anything for chance, right? If riser working is fine, if riser not working for any reason, then this one could be another consideration while doing the casting process, to be sure the process done perfectly without any issue, right? Then 107 اللي هو الدايمنشن دي. This is 107 which is the diameter. This diameter is 107. Then 107 here become increase here up and down. Then 107, this 107 increase up and down here. Also 1% of 208 minus 56. This is a 208 minus 56, meaning this length. Then you get here increase here up and down, and so on. Then every dimension will added this draft allowed. This is kind of, it's very simple actually. Let me tell you, this is done automatically by the computer in a software. As I told you before, we have whatever we call Magma software. This Magma software being used in a casting. Whatever you do, you make the drawing, you put the drawing in the drawing of the parts that you would like to have in the Magma software, and then Magma software usually added all dimension based on what we described here. Then finally get the final dimension The pattern, this is the pattern dimension actually. This is the final dimension. This is actually the pattern dimension. Pattern is the pattern that you manufacturing to create the cavity in the mold. So this is a pattern dimension after you added machining allowance, shrinkage allowance, and draft allowance. This is the one used to create the cavity in the mold. And finally, when you do the casting, then after machining and after shrinkage, then after you put all the pieces in, the part will satisfy the condition of the design without any defect. Right. This is a design consideration. Actually, this is the conclusion of what we described. Please read it. It is you find it is the conclusion of what we described in the chapter. And I would like to conclude this chapter with this figure. And this figure shows that this is a die casting, this is a sand casting, this is a plaster casting, this is permanent mold casting at number of pieces. This is the cost relation between cost and number of pieces you produce by casting. This is 1, 10 pieces, 100, 1000. This is 10,000, 100,000, and so on. You can see that if you producing small amount, 10 pieces, for example, if you would like to produce 10 pieces, you can find that if you would like to produce 10 pieces, then based on the cost, you can see that sand casting and the plaster casting, which is expandable, both are expandable, both the casting are visible. It's good to use. Permanent mold is totally not visible. I mean, cost is high here. But whenever you increase the number of pieces, you can see that if you'd like to manufacturing 100, you can see that still also you can use either permanent mold, or you can use sand casting, or even plaster casting. But if you increase the number of the pieces to 1000, you can see, if you increase the pieces to 1000, you can see that this is permanent mold is a solution. Sand casting and the plaster casting is, this is a cost matter of view. In a cost matter of view, time is really very time consuming, but cost matter of view, you can see that permanent mold is more visible. If you increase more to 10,000, or if you increase more to 100,000, then you can see that permanent mold. It's die casting is a permanent mold also. This is a permanent mold, general permanent mold. This is a die casting, which is one of the permanent mold. Die casting here is very visible when you have very high production rate, 100,000, you take million and so on. Then this one totally invisible. You cannot use sand casting and the plaster casting. It will be totally not visible to be used here with the casting. So this figure show you the relation between the number of pieces you would like to produce and the cost of the production, and based on that you can understand based on the number of pieces you would like to produce what is a suitable method to use in a casting process. Right? Any question? This is the end of the chapter 8, which is a casting processes. Any question generally? Okay, so this is the end of this chapter. Right. Let me move to next chapter. Right. Okay, we finished introduction and economy, finished already. Casting fundamental and process already finished. Now we're going to talk about joining and assembly process. Talk about the welding. This part is two chapters, chapter 25 and chapter 26. We're going to start with chapter 25. Okay, chapter 25, which is a fundamental of welding, right? Overview, we'll talk about overview of welding, the weld joint, physics of welding, feature of fission welding joint. This is the item that we're going to cover here in this chapter 25. Joining, we have whatever we call is permanent joint and non-permanent joint. Permanent joint, and we have whatever we call non-permanent joint. Let me explain. Actually, this is a joining process. Generally, this is a joining process. We have permanent joint, we have non-permanent joint. Actually, I described that earlier in chapter 1 in introduction. Permanent joint mean very difficult to disassemble again once it done. Very difficult. يعني بالعربي يا شباب لما تعمل البيرمننت جوينت، بيرمننت يعني دائمة، الوصلات الدائمة، لما تعمل الوصلة الدائمة بيبقى من الصعب جدا انك تفكها تاني. Once the permanent joint done, it's very difficult to disassemble this permanent joint. Like welding, we talk about the welding and riveting. Welding and riveting. Non-permanent joint, which is a bolt and nut. Non-permanent joint يعني الوصلات اللي ممكن ان احنا نركبها ونفكها. Easily to assemble and easy also to disassemble, which is a mechanical fixing, which is a bolt and there are many applications for this case, and also there are many other applications in the other case. So permanent joint and non-permanent joint. This is generally in the joining process. We're going to focus about the welding process as a permanent joint. When we talk about the permanent joint actually, this is a permanent joint. When you have permanent joint, in a very simple way, we do permanent joint here between the two parts. This is part 1, this is part 2, and here we somehow we make a permanent joint here between the two parts, and finally after the process finish, as you can see here, the two parts become one part, and then it is difficult to destroy this one, difficult to disassemble. If you would like really to disassemble, then you need to break this joint. Not easily to disassemble. If you would like, then you have to destroy the joint, as you can see here. Welding process. Let me say that welding process is the 3 types of welding process. Please give me your attention. Please give me your attention. This is very important. I hope you focusing with me. Welding process, 3 type of the welding process. Liquid state type. This is a liquid state. We call it fission welding. We have solid state welding. We have liquid solid state welding. There are 3 types of the welding: solid state welding, liquid state welding, which we call it fission welding, liquid solid state welding. Let me explain one by one so you can understand. So please give me your attention to understand what is the difference. This is very important. This is very, very, very important. So please give me your attention to understand what is the difference between these type of the welding. I start with the liquid state welding. Liquid state welding actually, when you said liquid state welding, this is the liquid state welding. This is the liquid state welding. In the liquid state welding actually, we heating the welding zone. We heating, melting the welding zone. We heat and melting the welding zone here. You can see that. Then you get liquid mix. This one become liquid, only welding zone, not everywhere, but only welding zone. Then you get liquid mix. This one become liquid, this one become liquid. You get liquid mix. While solidification, the part become solid. So this what we call is the liquid state welding. This is the liquid state welding. We call it fission welding. So this is a liquid state welding. The liquid state welding, you heat, you melt the welding zone for the 2 substrate. You melt the 2 substrate. Substrate يعني الاثنين الجزئين اللي انت عايز تعمل لهم welding. You melt the 2 substrate, you get liquid melt, and then you get liquid melt mix, and then while solidification, welding will happen. And then many ways to do this one. which is the resistance welding, electrical arc welding, high energy beam welding, thermal welding. This is the different type of welding under liquid state. In all these type of welding, we melt in a very simple way. We melt the two substrate material, and get liquid mix, and while solidification well done. The next type or the other type is solid state welding. Solid state welding, there are no melting. Solid state welding, no melting. This is a solid, this is a solid. And no melting at all, will not melt. This is, we're going to weld solid, and no liquid here. No liquid at all. We apply pressure, we apply high pressure. When we apply high pressure, then you get material like this. Each material, they are compressed against each other. Then you get the surface contact, very good or excellent surface contact. This is the way you apply pressure, then you get surface contact. You get increase the surface contact, you leave it for a while. When you leave it for a while, it will be like this. Material diffusion will happen. Elemental migration will happen, and diffusion. Elemental migration between these two materials will happen. Elemental migration, if you leave it for a while, then elemental migration between these two materials will happen. Elemental migration between these two materials will happen, finally leading to weld. Then you can see that initially this is under microscope. Initially, when you apply pressure, when you look to the surface, you find a little gap. Even this one is very small, but you find a gap here. When you leave it for a while, you see that elemental migration, atoms will migrate from up to down and down to up. Then you get material will diffuse in each other, and finally full diffusion will happen, and then you get material well done in these two material, as you can see. This we call it is solid state welding. Then why we call it solid state welding? Because no melting. Because no melting, we are not going to melt the two substrate, become solid. No melting at all. So please differentiate. This one liquid state, we melt the two substrate here. Can you see that? We melt here, we melt this one here, then you get a well done here based on liquid mix. This is the liquid state welding. Solid state welding, there are no melting at all. Someone will say that this one very fast. You can see that this one very fast. I mean the liquid state welding very fast, easy, very fast, very short time to do the welding. This one take time. Yes, it takes some time, because you have to keep this one for a while, then this one will happen. So why we have to do the solid state welding? Liquid state welding is fine. Why we have to go for solid state welding? Actually, listen to me carefully, please. Listen to me carefully. There are very important advantages of solid state welding over liquid state welding. What is this big advantages? Actually, liquid state welding only limited for welding similar material. Liquid state welding only limited for welding similar material. يعني بالعربي يا شباب liquid state welding فقط can be used for welding similar, يعني same material, steel مع steel, copper مع copper, aluminium مع aluminium. Cannot weld different material. No way to weld different material. Cannot weld steel مع aluminium. No way. We cannot do this. Must weld similar material. Someone will ask why? Why liquid state welding can only weld different similar material? Because here you can see that here in this, when you melt both material. Okay, for example, if you weld steel and aluminium, then you melt both steel and aluminium, fine, you get liquid mix. Okay, while solidification, every material will shrink in different way. يعني كل ماتيريال من التو ماتيريال لو هم different material will shrink يعني تنكمش in different way. Some material shrink in fast way, some material shrink in slow way. Then this one will shrink slowly, this one for example shrink fastly. Then you see that there are a big shear stress will happen in the area here, welding zone. There will be this one material will solidify, and there will be very high shear stress here leading to material separation, and then weld fail. Then again, there are many cracks. You get many cracks initially, and finally weld fail. Then all time remember, I'm not going to tell again, all time remember, liquid state welding is only or limited welding. Liquid state welding is limited to similar material. What about solid state welding? No issue. Can weld different material. Why can weld different material? Because there are no melting. We're not going to melt here. No melting and no solidification. You just apply pressure. And allow material diffusion. So if you have different material, like for example steel and aluminium, then no way, no issue. Then material diffusion will happen. Aluminium and steel diffusion will happen, and finally get bond done. Then this one is perfect solution. Let me tell you, solid state welding is a perfect solution to weld dissimilar material. Actually, let me tell you, there are a big challenge in industry in welding dissimilar material, and always there are a need in industry to weld dissimilar material. Perfect way to weld the similar material is a solid state welding. And there are many ways to do solid state welding, or many techniques to do solid state welding, like whatever we call cold welding pressure, diffusion pressure, hot welding force roller, and friction welding. This is a different way to do whatever we call solid state welding. Is it clear? Any question, guys? Any question? Is it clear the difference between liquid state welding and solid state welding? Please remember all time, this is really very important. Actually, I would like to draw your attention that welding really is very important for you as a manufacturing engineer. For example, in Aramco, they actually a lot of welding done there. Welding is really an issue, very important, and many engineers when graduated and apply. For example, I'm just giving in SABIC and Aramco and so on. When they go to interviews, they ask many questions related to the welding. I hope you feel that welding really very important, and many challenge usually in welding, and this is really very important information for you as a manufacturing engineer. So please just try to understand what is the difference between these kind of welding techniques, right? So we have whatever we call liquid state welding and solid state welding, and this is a big difference. So here you can see that this is the solid state welding is a perfect to weld the similar material, but the problem is the big issue, it takes time. How to improve in whatever we call is the liquid solid state condition. What is the liquid solid state condition? This is a question. Liquid solid state condition is liquid solid. So we have liquid solid. Liquid solid, what is the liquid solid? Liquid solid, actually we are not going to melt the two substrate. This is the two substrate, will not melt the two substrate. We will add another material in the middle. Here. This another material, we call it filler material, which is a black color. So we added another material in between. If you would like to weld this material and this material, two different material, definitely two dissimilar material, different material, aluminium and steel, for example. Then he added here whatever we call filler material. This filler material have lower melting temperature than both. يعني درجة الانصهار بتاعة الفيلر دي أقل من التو بيز material. And then You heat and melt the filler. You heat and melt the filler. Then filler become liquid. The both material become solid, and filler, only filler become liquid. Then while solidification, this filler material will diffuse in the material, first material and second material, and while solidification becomes solid, attaching these two metal together, then weld well done. This is kind of improvement of solid state welding. Solid state welding take time. This one easy and fast and cheap, more cheap than solid state welding. But the process here, the problem is that usually this one is weak. The bond here is weak because this material usually has low shear strength than in case of you have solid state welding. Then you can see that here this is we call it is brazing, soldering, and adhesive bonding. Brazing, soldering. This is whatever we call brazing. Brazing, soldering, and adhesive bonding are the technique, and this is the foreign material. This is the material one, this is material two, and this is the weld material, are different material being used to melt and weld these two different material together. Any question? Guys, any question? Right. Solid state welding. This is explaining solid state welding. Actually, in a solid state welding, before we go, yeah, we apply and leave for a while. But if you would like to fastening the process, heat this two material. Why heating? Because this fastening the migration, because it's mainly related to atomic migration between the two material. Then if you make it faster, if you would like to make the process faster, then simply heat the two substrate. When you heat the two substrate, material will quickly migrate from one to other, then bond will create it in a faster way, but no melting. We just heating the two substrate to energetic atom to quickly migrate from one to other, then easily you can do the solid state welding. This is the description here: solid state welding, liquid state welding, and solid liquid state welding. This is the description as we discussed now earlier. Then you can see this is the relation in a welding process, relation between the pressure and temperature. Pressure and temperature. If temperature, actually, this is the melting temperature. This is the melting, this is the 0.5 melting temperature. If melting temperature, if the temperature increase up to the melting temperature, if temperature increase up to the melting temperature, actually no need for the pressure. I don't need the pressure at all. I don't need the pressure at all, just only to fix the two parts that you would like to melt. No need for the pressure, and only you melt, you get liquid mix, and then you get well done here. This is the vision welding. This is the vision welding. Vision welding means liquid state welding here. But here, if the temperature reduce and the pressure increase, if no temperature at all, the pressure is very high. You can see that this is a cold pressure welding. If no temperature at all, then the pressure is high, and time also need time. But whenever you increase the temperature here, pressure is needed, pressure is getting less. If you reach up to 0.5 melting temperature, this is a diffusion welding actually. Diffusion welding usually done at 0.5 melting temperature. As I told you, why we increasing temperature? Increasing temperature to help assess the solid state welding, energetic the atom, to allow atom to quickly migrate from one to other, quickly migrate, and then process well done in a shorter time. So this is the diffusion welding happen usually at 0.5 melting temperature. Okay, this is the relation between the pressure in a welding, pressure and temperature in a welding. Why welding generally? Generally, welding is a permanent joint. Welding is a permanent joint. Permanent joint mean when you do the welding process, it is very difficult to disassemble this one. Why welding is important? Generally, why welding is important? It is important because weld component become a single entity. Single entity mean after welding, the two parts become one part, not two anymore, become one part. And usually this is the most economical way in joining in industry, very cheap compared with the other processes. Even mechanical fastening process is more expensive. Even mechanical fastening usually require additional hardware, and this one more costly. The economical way for assembly is a welding, and it is not restricted to factory, but also in a field also. That's portable system you can take to the field and do the welding in the field. This is why it is important. Limitation of the welding, as I told you, it is difficult to disassembly. Once this one done, it is difficult to disassembly. Most welding operation require expert, I mean labor, the technical, the skilled labor to do. And most welding process utilize high energy, and welding joint don't allow convenient disassembly, very difficult. And weld joint can have quality defect. Quality defect because in a welding, as I told you, quality defect, quality defect. So in a welding, as I told you, it is liquid mix. You melt the material, and in a welding zone, not all material, but you weld the material actually in a welding zone. Then when you melt the material in a welding zone and get liquid mix and allow solidification, some defect could happen like cavity, like porosity. It's very similar to casting. And there are some defect, casting defect, similar to welding defect. Well, I will show you about the quality defect of the welding at the end of next chapter, which is chapter 26. We will describe and we will discuss the weld quality and how to improve the weld quality to avoid having a defect in a welding after the process. And some of these defects usually difficult to detect. I'll show you also how to detect the weld defect. Right, this is the limitation and drawbacks of the welding process. Overview of welding technique. Right. This is the weld actually. Generally, this is the weld you get here, liquid mix. As we described on weld solidification, you get the weld done between the two materials. We're going to focus here in this subject. We're going to focus about the vision weld and solid state welding. Vision weld, which is a liquid state welding, and solid state welding. We're going to focus in these two items, right? Vision weld is a liquid state welding. So joining process. Vision welding is a joining process that melts the base material. This is the one material, this is another material. We melt here. We melt here. We melt the two base material. We heat the two base material. We melt the two base material in a welding zone. You get liquid mix. While solidification, you get the weld done. This material become material, and then you get the weld done here. This is a vision welding or liquid state welding. In many vision welding, please listen to me carefully, guys. Please listen to me carefully. In a vision welding, in many vision welding, filler material, we need to add filler material. We need to add filler material. This is whatever we call filler material. Can you see that? This is a filler material. Filler material will be melted and deposited here in vision welding. Why? Why? Because actually some material here, while you heating these two base material and get liquid mix, some material will be evaporated. No way to control. Actually, it is unavoidable. We cannot just guarantee that there are no material will be evaporated. No guarantee actually. Then some material will be evaporated while you're melting this kind of base material. Some material will be evaporated. How to compensate the material evaporated? Then you need to filler material. You need to melt the filler material and drop fill material liquid here to compensate the material lost in the evaporation. The question is, what is the filler material? Filler material must be must be same material, because here we said that vision welding is limited to similar material. We cannot weld this similar material. Even the filler material that you use must be compatible with the base material. Is it okay, clear? Then vision welding filler material is added. We added filler material to melt to the melting pool, here, as you can see, to facilitate the process and provide mean to compensate the evaporated material, then provide bulk and added strength to the welding joint. So it's very important. This one is really very important. We must add it filler. However, some vision welding we don't add it filler. Some vision welding we do not add it filler. We call it autogeneous. Someone will ask me why we don't add it filler. We need to compensate. This one I will show you later. I will describe these kind of not common cases, very few cases in a vision welding. We don't add it filler for some technical reason. And then in these cases, we call it autogeneous. The word autogeneous, when you find a word autogeneous, it is a vision welding with no filler material. Autogeneous mean filler, no filler in vision welding. Vision welding with no filler material. Right, so this is vision welding. This is vision welding, which is a liquid state welding. Right. Liquid state welding could be done by using arc welding, by using resistance welding, or oil gas welding, beam welding, and laser beam welding, electron beam welding, and laser beam welding. Right. All this technique, if you look to this technique, vision welding, arc welding, we're going to use electrical arc welding to heat the material and melt the substrate. Resistance welding, we're going to use electrical resistance to heat and melt to substrate. X-foil gas welding, this is a gas welding. We're going to fire a gas to get flame. We're going to use a flame to melt it to substrate material. Electron beam and laser, we're going to use the power of electron beam and laser to melt it to substrate. In all cases, you can see that my target or our target is to melt the two substrate material to be able to get liquid mix, to be able to get the weld done. So in all cases, either arc welding, resistance welding, flame welding, beam, laser, and so on, the main target, we use different ways, different power, different technique to finally melt the two substrate to do the welding process. Right. For example, we'll discuss about the arc welding. In arc welding here, we're going to use the electrical discharge. Electrical discharge. We connect. This is the electrode. You can see that this is the electrode. This is the workpiece. We connect the electrode and workpiece with the electricity. Then electrical discharge happen between electrode and workpiece. Then when you get electrical discharge here, then electrical energy will transfer to heat energy, heating the two substrate initially like this. After welding, this area will be melted, and here, this is the filler here will be melted and deposited in the liquid pool. Then you get well done at the process at the end of the welding process. This is as an example. This is an example, which is this kind of arc welding as an example. Let me actually end this class and showing you a nice video. Let me show you a nice video. It is short one, will not take time. This is This is the arc welding, as you can see here. This is the electrode, this is the workpiece, and this is the filler also. It is electrode and filler. It is electrode being used and electrode and filler. You can see that electrode here, it is the electrode discharge happen and material. This is a filler material. As I told you, material here, filler, this is a liquid. We melt the two substrate and we drop filler. Filler here, as you can see. Filler here, which is electrode. Electrode depleted and melted. Then you can see electrode here, we melting here, we welding the two material here in the middle. This one drop liquid, as you can see, melt and drop liquid in the welding zone. This one same material. This one, you must remember that this kind of arc welding or generally vision welding is limited to similar material, not dissimilar material. So this is a filler. It is a filler and electrode same time. And you see that this is a gas, this is a flux. Flux here coated with the flux. This flux actually also melted and create a gas here. We call it shelled gas. This one is now solidified. When solidified here, you can see that this well done and material become, as you can see here, you get the well done at the end of the process. Right. I hope you understand that. Okay, so go back to the slide again. Right, so this is vision welding. You can see that vision welding after the welding process. This is the well done here, as you can see. This is the well done here. Then when you see this is the well done here. This is some defect weld. This is the weld with some defect. This is a complete weld with is good condition. We investigate. This is a good weld. This is a defect weld here. We will discuss this later when we come to the weld defect. Generally well done between the two materials, and when well done between the two material here, it is completed as you can see in the figure here. This is vision welding. The hazard in a vision welding is ultraviolet radiation, which is dangerous. People usually wear a special helmet here to avoid the effect of the ultraviolet coming from this one, and smoke coming also. They put duct here to absorb this smoke to not affect this person or operator working in a welding. This is whatever we call a special hazard in arc welding. Next is a solid state welding. I will stop here. Time is finished. Then I have to stop the class here, and next time inshallah continue discussing about the solid state welding.